Hello everyone, and welcome to my SP2 channel. We're going to be talking about hybrid orbitals. This topic is one of my favorite topics of all in chemistry. Okay, they're going to be a little bit on the introduction for this interesting discussion. We're going to be looking at the SP2, and SP3 hybrid orbitals, and I will give you a really nice summary at the end of this lecture. Okay, stay tuned for that. Okay, so let's get started by introduction. Okay, so let's start talking about what does hybrid mean? What does this term mean, right? Hybrid. So I have a couple of simple examples for you. Let's say you've got a hybrid car. Okay, that means you can start your car either by electricity or by the simple petrol, right? So there are two different sources of energy for that car. Or for example, in biology, if you got a hybrid animal, right, it's a result of, let's say, crossbreeding of two different animals. So for example, a mule would be a crossbreeding of a male donkey and a female horse, right? Something like that. And they're going to have, their characteristics are going to be a little bit from each of these two parents, right? Which is really interesting, right? Now, similarly in chemistry, if you got hybrid orbitals, it's going to be a fusion of atomic orbitals combining aspects of their shapes and their size, right, to form a new set of orbitals with mixed characteristic. Okay. Okay, so a little bit more on the next page. Okay, so thinking about your Vesper model, right? So remember we talked about this model and we said that we can use this model very effectively to understand the molecular shapes of our molecule, right? But it's not going to be helping us understanding the atomic orbitals structures, okay? So for example, if I have something like methane, CH4, it has a tetrahedral geometry, right? But carbon in your CH4 has 2s and 2p orbitals, right? So there are two different types of orbitals here. Now, if you looking at these two orbitals differently, then the four CH bonds in our methane shouldn't be identical, right? But experimentally, we know that they're going to be all exactly the same bonds, right? They're going to have identical length and strength. So how this is possible? If they are using different orbitals to make these bonds, how come they all four are exactly the same bonds, right? So to answer this question, follow me on the next page. Okay, so to understand why we have identical bonds, the chemist thinking about idea of hybridization, where we have the atomic orbitals that are mixing and they are forming hybrid orbitals. We have new shapes, right? And these shapes are going to be aligning with the molecular geometries, okay? This mathematical process maintains the total number of orbitals, right? While we are creating, orbitals that are suited for understanding of our different bondings, okay? They're going to be three, actually not three, they're going to be different types of hybridization. The three of them are pretty common, which is SP2, and SP3. We can have higher than that, but in this lecture, we're going to be only focusing on these three that are correlating with the molecular shapes such as linear, trigonal, planar, and tetrahedral geometries. And this is an amazing connection between the orbital overlap theory that we have in our previous lecture, right, and the Vesper predictions. Okay. Okay, so let's talk about the sp hybrid orbitals first. The example that I have for you is BeF2. Okay, now starting by your Vesper prediction for the geometry of this molecule. I have my beryllium as the center, so that's your central atom, and it forms two single bonds with the two fluorines, right, the two fluorine atoms. And according to this theory, to the Vesper theory, this is going to be a linear geometry, right? And the bond angle has to be 180 degree. Okay, cool. Now, if you look at the electron configuration of beryllium, right, we know that the ground state is going to be 1s2, 2s2, right? So that means both of these electrons are on the same orbital, right? We don't have any unpaired electrons in the valence shell, right? Which means that it shouldn't be, capable of making covalent bonding, right? But we know that this molecule does exist, okay? So how is that possible, right? So what happened here is the hybridization is actually helping us to figure this out, right? We are assuming that we have hybridization happening for the beryllium's atomic orbitals. And what happened here is your beryllium is going to promote one of its 2s electrons, right, because we have two of them, to an empty 2p orbital, resulting in this kind of configuration. Now we have 1s2, 2s1, 2p1. So now as you can see, there are two electrons that are unpaired, right? The 2s and the 2p orbital is going to mix, and they're going to form two equivalents of the sp hybrid orbitals, right? So something like this, looking at your, s orbital, right, which is the spherical shape, and then you've got the propeller shape, which is your atomic p orbital. These are going to hybridize, and they're going to make two sp hybrid orbitals, right? You can kind of superimpose them, and that's how you can get the very last picture, okay? Okay, now that we have the sp hybrid orbitals, we can actually understand the formation of the bonds in this molecule, right? So the two hybrid orbitals are going to be oriented 180-degree apart, giving us the linear shape as we expected, right? And what happened here is each of these sp orbital, right, in your beryllium is going to interact with the 2p orbital from fluorine, right? And they're going to make two identical sigma bonds, right? And I'm just going to show you something as simple as this, right? So here is my p orbital from fluorine interacting with the hybrid orbital of beryllium. So that would be one, sigma bond over here. And I have the exact same thing on the other side, right? These two bonds are going to be identical, and they're going to have the exact same strength. Okay, so let me summarize the sp for you on the next page. Okay, so for this hybridization type, which is the sp, the molecular geometry is always linear with a 180-degree bond angle, right? They're going to be two sigma bonds that are forming by the sp-p orbital overlap, right? And the hybridization here is helping us to understand why beryllium can form two identical bonds despite having only one s orbital in its ground state, right? Okay, I hope that makes sense. Let's take a look at the next page. Okay, now we're going to be looking at the sp2 hybridization, right? So to form the three equivalent sp2 hybrid orbitals from 1s and 2p orbitals, right, for bonding, which is going to give us the trigonal planar molecule, something like C2H4, we need to have the following, okay? So I'm going to walk you through these steps. Bear with me, okay? So the first step is starting with the 2s and the 2p orbitals that we're hoping to have the overlap. We're going to have the promote of one electron, right? Typically, that's what we need. We're going to mix the 1s with the 2p, and that would give us three sp hybrid orbitals, right? The remaining p orbital, because typically we have three, we already have used two of them for hybridization. The third one is the one that we later use that for our pi bond formation, okay? And it's going to be always the trigonal planar where we have 120-degree angle, right? That's the bond angle. And the picture would be something as this. So this is the S, and you have the two P's, right? And they are giving us these three sp2 hybrid orbitals. If you put them all together, kind of superimpose them, it would be something like this, okay? Okay, so we're gonna have kind of similar discussion for the sp3, right? Now we have, four equivalent sp3 hybrid orbitals where we have 1s and 3p orbitals that are mixing, right? These are the ones that are forming our tetrahedral shaped molecules, something like methane, right? So here are the steps. We're gonna start with like 2s2, right? 2p2. That's what we have in our valence shell. Typically, we need to promote one electron, right? So to turn that to 2s1, 2p3. Then we are mixing these orbitals, right? So 1s and 3p. are going to all hybridize, and they're going to give us 4 sp3 hybrid orbitals, right? Each of these hybrid orbitals are going to form a sigma bond, right? The geometry would be tetrahedral, and we're going to get the 109.5, which is a very exact bond angle here. And take a look at the picture, right? As you can see, you've got your s orbital with all of these p orbitals that are kind of hybridizing, and that is giving us 4 sp3 hybrid orbitals. We can put them all together, which is going to be our last picture here, right? Okay, excellent job, everybody. Okay, so let's summarize everything. There are going to be a couple of slides for a summary. Okay, so starting by this one, how to describe the hybrid orbitals used by an atom in our bonding. So our job is to start by drawing the Lewis structure, right, for either the molecule or the ion, depending which one is given, right? Then we're going to go ahead with the Vesper model to determine the electron domain geometry around the center, right? Then we're going to specify the hybrid orbitals needed to accommodate the electron pairs, right, needed for that specific, geometrical arrangement. Okay, cool, cool. So let me show you a nice summary table on the next page. Okay, so looking at this nice table, you've got everything summarized. We have the sp, that's our atomic orbital set, which is going to give us 2 sp hybrid orbitals, right? And that's how we can get the linear geometry. The example is something like BEF2, right? The other one is where we have S, P, and P, which is going to be the sp2. That is going to give us 3 sp2 hybrid orbitals, right? The geometry would be trigonal planar, right? Something like SO3 or BF3. Then we have the S, P, P, and P, which is going to be the sp3, and that would give us 4 sp3 hybrid orbitals. That's what we have for like tetrahedral molecules, something like water or even methane, right? So keep that in mind. The number of atomic orbitals is going to be always the same as the hybrid orbitals. So if you start with 2 atomic orbitals, right, we're going to get always 2 hybrid orbitals, right? Okay. Cool, cool. Thank you so much for watching this video. If you like it, give it a thumbs up. There are going to be a lot more coming up for you. Okay, take care of yourself, and I'll see you around. Bye for now.